Hey there, and welcome to 16.1 Vector Fields. This is not how I thought we'd be starting Chapter 16, but hey, if the pandemic gave us some tools, we might as well use them. So this video will be just a quick start to hopefully get you introduced to the idea, and we can lock down any questions when I'm back in person. But so Chapter 16 is about vector fields, and a vector field just assigns a vector to a point in space. So let me just say that, so far, mostly, we have dealt with some vectors already, but so far mostly, when you have a function of x and y, and when you plug in a point in space, like the point 5 over and 2 up, you plug that in and then you get a number result. So regular functions assign a number to a point in space, and that's great. That might represent the temperature at that point, or the kinetic energy, or whatever else. And now we'll have a function still of x and y, but that function will be designed to produce a vector so that when you put a point in, the result is not a number like 16, but it's a vector like 1, 2. And keep in mind we have another notation, which is the ij notation, so that could also be 1I plus 2j. Either of those is fine, but what that means is for the particular location in space of 5 over and 2 up, at that particular point in space, there is assigned to that a vector, the vector 1, 2, the vector that says, here, let's switch colors. The vector that says 1 over and 2 up, so it looks about like that. I haven't told you what the vector function is yet, but if we knew what it was, we could keep going, right? I could plug another point into it, like maybe 5, 1, just for fun, and suppose out of that comes negative 2, 1. I'm just making that up. So now you could say for the point 5, 1 in space, right there, there's a vector at that point also, and that vector happens to be wildly different. It goes negative 2 back and 1 up, so it actually points over this way. And I could keep going with this, and produce vectors endlessly for the infinite number of points that there are in two-dimensional space, or in three-dimensional space for that matter. And these vector fields can represent lots of things. Some standard sort of applications of vector fields are fluid flow things, so maybe wind speed. This is kind of an artistic representation, but maybe this is maybe more standard weather map with vectors at various points representing the wind speed there. So it could be wind speed or ocean current speed, temperature change vectors, magnetic force is another one that is often represented with these iron filings type pictures that I think are very cool. But anyway, you get the idea. There's lots of applications. We should look at a couple examples. So here's the first few problems from the homework. I'm sure they would like you to sketch these by hand. However, I'm going to have you sketch these with technology instead. So if we were going to do number 4 by hand, I think we would go through and we'd make some x y points, and then we would get the vector result, and we would just start picking points. So we would say, oh, how about at, at 0, 0, what's the vector you get? And you plug 0 in for x and y in this vector equation. So 0 minus 0 is 0, and 0 is 0, so you get the vector 0, 0. And if you use a point like 1, 0, plug 1 in for x, 0 in for y, now you get the point 1, or sorry, the vector 1, 1. And when you plug in a point like 1, 1, you get 1 minus 1 is 0, and 1, so 0, 1. So we've now got 3 vectors that we could plot. So at 0, 0, we should plot a vector with a length of 0. At 1, 0, right here, we should plot a vector that goes 1, 1, about that direction. And at 1, 1, at the point 1, 1, right there, we should draw a vector that goes 0 over and 1 up. So there's 1, 2, 3 points in space with their associated vectors. Of course, this gets tedious incredibly quickly. So I do not want you to do these first few problems by hand. What I'd like you to do is to use the vector field graphing app that I mentioned in a previous announcement that I will also link on the 16.1 Canvas page. And just use that to get a picture and then give me a quick sketch of the picture. So let's see if I can track down where I've got that one, I think is here. So this is a vector field sketcher. If you have a different one you like better, of course, you're always welcome to use that. But we just need to put in the x component. So that would be x minus y for number 4. And the y component is the x coordinate. And we should, there we go. I should have it. The vectors are all a little bit short right now. Let's see, where is the vector height? Oops, that's the vector. There we go. Okay. We can sort of relatively scale all of them. So put them somewhere that makes it comfortable to you. Yeah, that's too much. There we go. So either just put a screenshot of this in your homework, or if you feel like doing it by hand, just take like 20 seconds to try to give me a sketch of that by hand. Like don't get too precise, just give me the general feeling. Really what I want you to get out of these first few problems is just the fact that you can graph vector fields, and that each vector comes from plugging into some particular function. So as long as you get that much, I'm happy. Okay, so that's the first few homework problems actually, and let's move on to the next little chunk, which is matching. And of course, you could just grab the graphing app and just graph all 4 of these and match them up, but you'll get more benefit out of this if you do it without the graphing app. So hopefully at this point you can say, okay, what would a vector field look like if the x component of the vector was the y coordinate of where it begins, and vice versa. Or for number 12, you can say, well, apparently for number 12, all of the x components are 1. So every single vector from its start goes over 1 and then goes up or down by amount determined by sign. So you can see, are there any of these where they all seem to go over 1 and then up or down some? And I'm waving my pen around over option 4 here, which might give you a little bit of a clue, but hopefully you can just kind of feel your way through those 4 with the process of elimination and a little bit of thought about, if I'm at the point, 3, 3 basically, what should the vector look like there? You can say, 3, it should look like 3, 1/3 if it's number 14. So you can think about that. 2. Okay, so there's a little bit of matching for 11 through 14. 15 through 18 does the same thing, but it's in 3D. So you can, of course, do 3D vector fields as well. If you're in 3-dimensional space, you have an X, Y, Z inputs, and then you put those in, and it produces a 3-dimensional vector. That's way harder to graph by hand, by the way, impossible to graph by hand, essentially. So you will want some sort of graphing app if you need to graph some 3D vector fields. I did give you a link to a 3D grapher as well, although I don't think you'll need it for this homework. But hopefully still you can look through number 15, for instance, say, for 15, apparently all the vectors are 1, 2, 3, no matter, there's no x's or y's or z's involved on number 15. So for 15, you should be looking for one where every single vector is the same. 16 should be similar. The x should be 1 and the y should be 2 for all of them. But the up or downness of the vector now is determined by the z-coordinate of the location of the vector. So vectors that start higher in space should be steeper because they'll have a big z-coordinate, and vectors that start at a height of 0 should have a 0 z-coordinate, and vectors that start at negative places should be pointing downward. So you can see if there's one of these 4 that seems like that to you. So hopefully you can trace your way through that also. And the last chunk of what they're going to ask you to do is to match again, but they're going to use new terminology here that we haven't talked about yet. So here's the last new thing that you need to know for this homework. It says match the plots with their gradient vector fields. And they just give you regular old x, y functions, which don't produce vectors. They just produce numbers, right? But we do know for a function like x, y that function has a gradient. Right? I know, taking you back a little ways. But remember that the gradient in general is the partial derivative with respect to the first variable and the partial derivative with respect to the second variable, and if there were a third variable you would keep going. But for our particular function now, one vector field that goes with it would be the gradient vector field. So we can say, what is the derivative of x, y with respect to x? You can say, well, that would be y. And what's the derivative of x, y with respect to y? And that would be x. And you're like, oh, now I can talk about a vector field that goes with the gradient of this function up here. So now I produce vectors that are the x-coordinate of the vector is the y-coordinate of its point in space, and vice versa. And again, you can think about which of these 4 pictures that looks like, and if you get super stuck, just grab the vector field grapher and graph it. But again, more benefit if you try to wrestle your brain around, okay, what would that look like if I was at the point 3, 1, the vector, so at the point 3, 1, here-ish, if it was this one, the vector should look like 1, 3. So it should look like 1 over and 3 up. Should look kind of like maybe that. Oops, 1 over 3 up. Why are you so curvy? Anyway, So it's probably not this one, but you can figure out one of these other vector fields that might look that way instead. So the gradient vector field will become important later as we sort of take regular old functions that are not vector functions and work with them using some of our vector tools and say what their gradient field can tell us about the original vector. Okay, so when I get back on Thursday, we will start 16.2, where we'll start doing some calculus with all this stuff, but this is just the introductory section. So hopefully this gives you a good start. I will see you Thursday.